Just to begin, I'll just introduce myself and then Helen can introduce herself. My name is Anna Koskol. I am an environmental educator at Hudson River Park. I've been working with the park since 2016, primarily focusing on leading all of our field trip programs, public programming, and outreach, educating New Yorkers all about this really wonderful ecological resource, the Hudson River Estuary. And I also support and manage a lot of our sustainability efforts, mainly plastics and plastic waste reduction, and also community composting. So I've been doing that for a while. My background is actually in psychology. I studied at Stony Brook University, and my background is also in early childhood education, working with students. So I'm really excited to get to know you a little bit more and share our work with you. I'll let Helen introduce herself.
Thanks, Anna. My name is Helen Polanco. I work here at the Hudson River Park as a field science coordinator alongside Anna. My main responsibilities are supervising our water quality instrumentation and supervising our microplastics research here, which you will learn promptly about, and other ecological surveys in the park. Another person. My background's in geology. I studied geology at SUNY Potsdam, and currently right now I am attending Hunter College, getting a master's in science in geoinformatics. So slowly turning into a data scientist slash, actually, I'll be graduating soon. So I will soon be a data scientist and a geographer and a marine scientist all at the same time.
Yay. All right. Thanks, Helen. So today we're going to talk about a few things. First, we'll introduce you to Hudson River Park if you're not familiar, and then we'll talk about plastics and how we kind of conduct our research. And then we'll talk a little bit more about microplastics IDing and how we conduct that, that process of really looking at the fibers and the plastic nurdles and all of that we find in our waters through our trawls. So Helen will explain all of that. And lastly, we'll touch on really the initiative that came out of this research, Park Over Plastic, an initiative to reduce plastic pollution in the park. So to not waste any more time, let's get right into it. So Hudson River Park is located on the west side of Manhattan. So that's from Chambers Street up to West 59th Street. And what's interesting is that most of the park is actually water. It's a 400-acre estuarine sanctuary, a protected habitat because of its biodiversity. So these are kind of the highlights of our park that we provide New Yorkers to really engage and interact with the water. And unfortunately, though, the park didn't always look like this. This is a picture of Manhattan's waterfront from the 1990s. I think it's like 98, I believe this one is. So these historic shipping piers that really are characteristic of the park, following the Industrial Revolution, they were abandoned and deteriorating by the 1950s, which really limited people from connecting with the Hudson River. This area was not inviting, and the public really had little reason to want to protect it. But thanks to the Clean Water Act of 1972 and scientists and activists, there was a lot of tightening of regulations for discharging pollutants up and down the Hudson River, which really helped to improve local water quality. So long story short, in 98, the Hudson River Park Trust was created through an act of the New York State Legislature to develop and maintain a new 5-mile waterfront park on the lower Hudson River. So what's unique about the park is that, it was created by scientists after scientists identified the park's pile fields, which are, the old piles that were left behind from the decrepit shipping piers, they were actually a key, and still is a key, nursery environment for critical fish species like the striped bass. And we kind of like to say that the striped bass is our mascot because they are an anadromous fish that begin their lives up in freshwater, but as they grow older, they come down to saltier brackish waters. They use the estuary as a nursery before they spend their adult lives in the Atlantic. So it's a very critical habitat for animals like the striped bass. So our team, Helen and I, at the River Project, we work to protect and restore and educate about this marine ecosystem. And we're reaching over 25,000 people, and students in all 5 boroughs come to us. So that's a really special space for us. And this is just an example of some of these renovated piers that we provided for the public. And when you visit the River Project at Hudson River Park, we're learning in all these different types of environments along the estuary. These are just some of the examples of different spaces where we conduct our research and run our programs on the estuary. So we got the Pier 26 tide deck, which is excitingly just recently opened. We have the wet lab at Pier 40, which is an open kind of native aquarium, flow through aquarium space, an education space. And unfortunately, last year we weren't able to open, but we will be having open drop-in hours this summer, which is great. We encourage you to check us out. And we also have more terrestrial environments like the native flora habitat garden at Pier 66. So all these different spaces to really provide people with a really rich, full experience of what a native local estuary waterfront can be like. So unfortunately, there are still some, water quality impacts happening because of its, proximity to New York City, because of its proximity to the greater watershed of the Hudson River. So the first one, some of you might be familiar with, combined sewer overflows and how wastewater really holds a lot of pollution coming from us. Historic contaminants, like I mentioned, the Clean Water Act really helped to reduce that, but that is still something we find in sediment in the river. And then pollution, just general pollution that can be found throughout the watershed. Like I said, the tributaries, the streams, all throughout upstate New York, all along the Hudson River, can impact and contribute pollution into the water. So what we're focusing on today, obviously, is the plastics that we find. And let's see this next slide. We all probably generally know the harms of plastic, and these numbers are probably not surprising to you anymore. But we really do see the impacts of our actions along the waterfront. This is a picture from our Gansevoort Peninsula taken, I believe this is 2-3 years ago. And you can see just, the variety of plastics that will one day degrade into tinier microplastics that will inevitably come in contact with our wildlife. So CSOs, as a review, if you're not familiar, 60% of New York City's sewer system runs on a combined system. And so that means that on wet weather days, which is about an average like once a week, although 2018 was a particularly wet year, so can be more than that. But wet weather events really disrupt the natural wastewater treatment system. And instead of the wastewater from our homes and from our storm drains going into the treatment plants throughout the city, it is overflowed out into our waterways directly before it can be treated. So this kind of diagram on the left, the dry weather, shows what it's normally doing, which is great. That water, can you all see my clicker, my pointer? Okay. The domestic sewage is entering our wastewater pipe, and that is diverted into our wastewater treatment plants. And this is kind of keeping that from entering into the effluent pipe. But on wet weather events, when storm drains are collecting excess water, that water is just triggering an overflow, a combined sewer overflow. So that's kind of what that CSO means. And in New York City, we have hundreds of them. I believe it's like close to 700 CSO points impacting, you know, they're pouring millions of gallons a week of wastewater. So you can imagine what kind of pollution is found there from our homes and from our streets. So that's kind of a topic that we often like to educate about, because that's where we as people have such an impact on, and something that we can change behaviorally to really reduce pollution. This is a cool map we pulled from a site called Open Sewer Atlas. If you're not familiar with that, I would suggest you check it out. It's really cool. There's a lot of cool maps on there on our local watersheds. So this is something called the sewershed map, which is, so all these brown dots are signaling the CSO outfalls. And the larger the circles, the higher volume of the wastewater that is coming out through CSOs. So, and then they're outlining the sewer shed that the water is being collected from. So this one, I like to point out, this is Pier 40. So this is where our offices are. We have a particularly large one here, Pier 40. If we look on this chart, sorry, not westward, Pier 40, 130 million gallons a year. And this is a pretty large area of land. Does anyone know what could be contributing to such a large output of wastewater? If you want, you can write in the chat, or if you want to speak up, whatever you want to do. What do you think is what's located in this area? This is West Washington Square. This is the West Village area.
NYU?
Yep, very good. So NYU campus is right here. So that's where we're seeing a lot of water usage. So yeah, this is a really, I think this is a helpful map to picture kind of the volumes and where they're located. Perhaps there's one located near your home. Perhaps you see something, you know, located near where you work or at school. And is there proper signage there? Do you see, we like to go out and look at the discharge that's happening during rainfalls. It's strange because sometimes it's not happening actively while it's actively raining. It's sometimes a few days or a day later, a couple hours later. So we always like to monitor that. And that's something we do as we conduct our research, is keep track of rainfall. That's a very big indicator, or we think that it is an indicator of discharge, plastic discharge. So next slide. Here we go.
I was wondering, could I ask a question, or do you want to save it for the end?
I can take a question real quick.
Okay, it has to do with the CSOs. Is this a system that, like, it's just built into the system? There's not much you can do about it? Or is there a way to, is there some kind of solution not to do that?
So, so there are ways that the Department of Environmental Protection, the state and the city are working to kind of retroactively create solutions, such as catchments, which is, you know, a filtration catchment in front of the CSO when it's pouring out. There's also the biggest impact would probably be when we are creating more green spaces, more of the rain gardens, the rain barrel program, collecting water in order to divert stormwater. But in terms of the actual infrastructure, it's in there good. It is in there, and it would take millions of dollars to fix or to replace. And this is something that has been, you know, way earlier when the city was just kind of growing, this worked because there was little, less people, so less water to treat, less rainfall because less climate change, so less flooding. And so it worked at the time when it was created. And this is the case with actually several other older cities. I think in Boston, I think San Francisco, some older cities have this as well. It was revolutionary at the time. And now, obviously, not so great. but it is something that would take a lot of effort and money to replace. And so currently, it's more about the retroactive efforts. But yeah, great question, because it's a bummer for sure.
Thanks.
Yeah, great question. Okay.
I
Go ahead, Helen.
In the chat to also expand on like why the sewer system was built this way and how long ago it was built. So the initial reason why it was built was because there was a cholera outbreak in the city, because the water was being sourced. This had been during the time before they sourced our drinking water from upstate. So as Anna said, this is like a whole revolutionary, movement at the time. And today, the DEP is working to like really add and edit all of the current infrastructure, as Anna mentioned.
Thanks, Ellen. Yeah, I forgot about that. Okay, so let's move to the next slide, which is just touching on, the main reasons why plastics are harmful to the environment and to wildlife. Plastics photodegrade, which means that they break down into small parts called microplastics from UV rays, or they break down faster in that way through UV rays. And so that really is not, it breaks down, but it's just breaking into tinier and tinier pieces. It doesn't actually naturally decompose into organic matter. And when they are broken down, they are releasing toxic chemicals that are affecting water quality, that affect the health of wildlife, and they can actually attract other toxic chemicals as like a magnet. And so as they break down even further, there's more surface area, and therefore more surface area for other chemicals to attach onto. And then there's the concept of biomagnification and bioaccumulation, which is really, that the chemicals are accumulating in the animals when they're ingested. And, the higher they are, the apex predators are more likely to get the most magnified amount of that chemicals because of, their position in the food web, and that's biomagnification. And then we all seen the classic turtles stuck in the can bottles, soda rings, and things like that. They're definitely ensnaring, and also birds are eating them and realizing they're not getting the nutrients they need, and they're malnourished. So those are kind of the top kind of concerns. And so what we're doing about it, there are several ongoing projects happening. One is our marine debris or macroplastics research. And this is really, all of our research is focused on community science and involving our partners, involving the community to participate in order to learn and helping to collect the data. So we conduct shoreline cleanups. We are mostly piers, so we actually just have 2 soft shoreline sites that we work from. So we are collecting data in the warmer months of the year, so generally between like March and November, and we're having monthly cleanups at these different sites, inviting the community to not only remove debris, but also count and categorize and collect some extra metadata on the plastics that we're seeing. So last year was obviously a weird year. We weren't able to do a full season. We just had maybe a handful of cleanups with really small groups of people. And even then we were, collecting over 3,000 pieces. We were able to conduct them still monthly, and then see the different variation of plastics. And we like to take a look at that. So the chart on the right is showing us the foam items are the most common. They've always been. Does anyone want to think about why? Why would the foam items be the most common that we're collecting? I need to be better about looking at the chat. They float. Yes, they float. So yeah, they're super lightweight. Exactly. So they're flying all over the place and they can end up everywhere. And they also can break down easier. They break apart into tinier pieces so easily. So we're just seeing it's really nonstop. It's almost like impossible to collect them all. So that's why we see foam pieces a lot. But thankfully, New York City, there is a ban on styrofoam food takeout containers for certain businesses over a certain size. And so that definitely helps, but we're still seeing foam as a long-lasting type of plastic. Beverage bottles, they're primarily PET. That's the number one type right here. We see that 84%. That's the most common type of plastic we see out of all the marked pieces that we see, just because they are the primary plastic item, most likely for our beverage bottles, our to-go cups, and even some of our to-go food containers. And we take all this data, and of course we take our own internal research and analyze it, but we also do contribute it to the greater national database. So for the National Oceanic and Atmospheric Administration, they have a marine debris tracker app. I would recommend use it if you're ever doing a shoreline cleanup, so that you're contributing also to a national database. And just this number here, over 29,000, this is just something that we've accumulated in terms of our research data since the start of this particular research, since 2015. So we're seeing a lot of plastics. And we hope to continue doing research on this. We hope to expand, and we hope to maybe even invite you guys one day to do a shoreline cleanup if that was of interest. Yeah, okay, so that's one type of research, and now I'm gonna kick it over to Helen, because microplastics is, you know, a huge thing, a huge concern that we've been, you know, working on for a while. So I think, Helen, you can maybe start by talking about microfibers. Yeah, the slide here.
Anna, just before you pass it over, we had a question from Sue. She's wondering, is the foam coming from packaging?
Yes, yep. So, well, by packaging, do you mean like packing peanuts? Because yes, but also what we see, we're guessing most of our debris on our shorelines is coming from CSOs or local activity. So most of ours, I would say, is either fishing or like coolers, or fish or boating related coolers that are styrofoam, or food like beverage cups, mostly like, you know, the Dunkin' Donuts cups or the takeout containers. So that's kind of what we mostly see. But yeah, we definitely also see packaging as well. Any other questions for me before I swing it over to Helen on microplastics? Okay. All right, Helen, you want to take it away?
Yep. So this is a good segue into microplastics, because from larger marine debris comes microplastics often. But first we're going to start off with microfibers. This is think of this part as sort of an extension of the CSO impact. So microfibers, what are they? Microfibers are pieces of plastic that are woven into clothes, bags. They're much smaller than microplastics. They're like a smaller, they're much finer and much smaller. And so when you wash something in the washing machine, often fibers from your clothes or your backpack or whatever it is that you're washing will go out. And it would go out from the washing machine into the wastewater treatment plant, and the wastewater treatment plant will treat the water, but it doesn't really have a screen that's fine enough, or processing that's fine enough to be able to capture all of them. some of them are really, really, really small. So they end up in the environment. And sometimes they also get caught in the sludge that is left behind, that is separated behind when cleaning the water. And that sludge is often used as fertilizer. So it gets like in the dirt and in plants, as you can see. And then like sewage sludge also gets dumped at sea. So these are some of the ways that this is what microfibers are, where they come from, and how they get in our environment. Currently, there's some products and some studies that have tried to figure out ways to mitigate this problem. There's something currently called like a Cora ball that you can put in your, I believe it's for the washing machine, and that it acts like a lint trapper. So from microfibers, I'm going to move on to our study, microplastics, our microplastics research. So our microplastics, so the Hudson River Park from 2016 to 2019, we have been surveying microplastics in the Hudson River at 2 sites at 2 locations from June to October, seasonally, every one of those years. So we would survey in the nearshore location because the idea was that nearshore locations would get more microplastics than the channel section. So downtown, we also surveyed downtown and uptown. So it was nearshore channel downtown in around Canal Street area, and then nearshore channel up around like the Hudson Yards area. We would use a 0.3 millimeter size Newson net to capture the microplastics, which had a 1 liter water bottle attached to it, and trawled it for about 15 minutes at each location. And once we captured that water, we'd put it in mason jars and send it out to a Brooklyn College lab to be processed using a wet peroxide oxidation process. Then from there, after they were processed and dried, we would use a stereoscope microscope to manually pick out pieces and categorize pieces of plastic that were around 0.3 to 5 millimeters in size. And we did that because that was the limit of the size of our Newson net. So we weren't really focusing on like microfibers because that's just not what our Newson net could catch. But they are like part of the category of line, and I'll get a little bit more on like under what category they have fallen under. But our study quantified the abundance of microplastic types, and I'm going to go into a little bit more of exactly what these types are. Oops. But we have the abundance, and the most abundant type that we would find a direct correlation between rain and microplastics for the samples that we took. It still seemed in a little exploratory line graph, you could see that like as it rained, microplastics did increase, but it just wasn't enough data to be able to make any kind of real correlation. So the next slide. But what we did find was that there was a difference. There was a significant difference between nearshore samples and channel samples, and specifically nearshore channels and samples taken in nearshore locations in 2018 were higher concentration than both channel concentrations in 2016, 17, and 19. You can see from this line over here, oh, you can't see my cursor, the top whisker of each one of these. The top whisker is the max observation. So even just looking at this box plot, you can see that for nearshore locations, it's always higher in concentration than the channel location for its respective location. Okay. So now I'm going to go a little bit more into like microplastics ID and the categories that I had mentioned earlier. So we have fragments, and what fragments look like are, they're like this unidentified hard, sometimes can have this like waxy texture. If you scratch it with a needle or something, it would get like waxy scratch. Nurdles, which are hard and rigid and sort of like you can't really bend them. Foam, as Anna described, soft and bouncy. We're all kind of familiar with foam. Line is categorized more as, so this is where fibers kind of falls under this category. Fibers are considered line. They're just they're often like looked at differently because sometimes they're composed of things like nylon, and are just like way smaller. So it's just to distinguish between the two sizes. Line is often thought of something that came from a net, or a rope. It's just a little longer and falls and was being caught by our net. But you can consider microfibers line as well. Most people are just calling line fibers nowadays. Pellets are hard circles of plastics, and then we have film that's like, I may be a little outdated here, but like film, you can think of it kind of it looks a little bit like an old photo film, like the ones that you used to like take a picture with manually, and then you pull out the negative, flimsy and stuff. Or if you are familiar with the mineral biotite or muscovite, a lot like that. And those come from things like those. Where would film come from? Where would that material come from? That would come from like your plastic water bottle has like a wrap around it often. So those things break down into tiny pieces of film in the water. And like I mentioned, fibers. And under our microscope, often we would find some like combined pieces that I like to call amalgamated pieces of microplastics. And I'm going to talk about how we used to deal with that when we saw it in our microscopes. You go ahead. So just to take a closer look at fragments and pellets, if you look at figure 1, you can see that there's this like kind of earwaxy thing over to the left. That's what a fragment would look like if you were looking at it under a microscope, stereoscope / dissecting scope. And pellets are these hard circular balls that you would see in figure 2. Then, sorry, just have the chat box over the screen a little bit. And then I have another example of like fragments can sometimes come in other kinds of shapes too, like this thick, like next to the waxy kind of orange circle, there's this thick tube-like plastic. Yeah. And that can also be a fragment because it's not very thin and it's like it's waxy as well. These things just break down from other fragments are the most abundant because they break down from the macroplastics, the larger marine debris, and they might come from degrading water bottles, degrading caps, degrading other types of plastic shapes, anything that's plastic that gets in the environment from photodegrading, and the water and mechanical degradation will cause larger plastics to turn into microplastics. So next slide. This is kind of an example of what film would look like. It's kind of like clear like this. And I'm sure that like if you took like a Coke, like a Pepsi wrap off, you could see like the clear side would sort of look a little bit like this. And then we have foam, and it looks really familiar, I'm sure. And it, like Anna said, it comes from like mostly those cups, like Dunkin' Donut cups, like the hot cups. So yeah, and nurdles. Nurdles are often also one that you would find a lot, and these are intentionally manufactured by cosmetic industries. They're put often in like skincare products, and they're often also used as kind of the creator of larger plastics. So companies will like melt these down and turn them into larger plastics, but somehow, sadly, still get in the environment. So the next slide.
Oh, I was going to add one thing. If you've never been to the Sims Recycling Municipal Recycling Plant in Brooklyn, I recommend you take a tour there. They do offer tours for organized groups, and they are awesome about showing the process of how they take the recycling of our plastics in our city and breaking it down. And you should get a tour of the way that it's being sorted. But one thing that they show is that they have these pellets or these nurdles of what Helen was just talking about, and the way that they break it down into these smaller little pellets that then they sell, or that is being used to melt back down to recycle that plastic. So you can see what Helen's talking about up close, and it's a cool facility to check out. Okay, next slide.
That's really cool. I should check it out. I've actually never been there. And this is what I was talking about, line. You can see line can be pretty long, and depending on its like, it's very identifiable. It looks like a long string. It often, it's under the microscope, it's like often like really obvious that it came from either a net or a rope. And fibers will sometimes, and fibers are often made of things like acrylic or nylon, like those synthetic materials in your clothes. And like the middle image here, it appears really familiar. You know, it looks like a fiber from like a fleece or something. So if you ever have like a small little, like, you know, earbuds sometimes come in a little like bag or something that you can put fibers in. I mean, that you can put like maybe a hat or any kind of small like clothing like material or a towel. You can like squish it around, and take the item out of the bag and see how many fibers are left behind. That would be a fun experiment for you guys to do at home. And sometimes in our samples, we'll find like organic and natural materials. So you may wonder, how do we distinguish between tiny pieces of natural organic matter and plastic material? Plastics are, they make a particular reaction to heat. They often bubble and melt really fast. If you heat up like a metal prod and get really close to them, you don't even have to poke it. You get really close and they start to just like boil away. Whereas usually organic material like rock and wood, they start to smoke. That's a good question. How much dental floss is in the water? That's a good observation. Lots of people tend to like put those down the drain. And as I mentioned earlier, when they get amalgamated together, we would just count them separately. We would just, as best as possible, sort of go around the ball and just count them separately and categorize them separately. Okay. Okay, next slide.
Oh,
yeah.
Okay. Done with that. Okay, awesome. So like I mentioned, Park Over Plastic is kind of this park-wide initiative that we've conducted starting in 2019 to really combat this from a behavioral standpoint. And so that means that we have kind of detected or selected these different audiences. We have our staff, the internal staff. We have about 100 staff working throughout the park, different departments, and how our culture around sustainability is impacting, the actions of others and how it's seen in the park. So that's one kind of bucket. We also take a look at our visitors. That's a huge audience, our public. And then we also look at our tenants. So the park has all of these different groups, tenants like boathouses, restaurants, some other groups that are actually paying rent in our park, and they are tenants of Hudson River Park Trust. And they are a group also that invite people to their spaces, and they are, providing services or selling products and being mindful of the way that, the plastics that they're using there. So this effort is to really focus primarily on single-use plastics that are meant to be only used once and then thrown out. That's really where the waste is coming from, like your grocery bags and your Poland Spring bottles. And finding solutions and really having that open communication to find solutions together and sharing best practices. So some of the things we've been working on in the first 2 years is increasing drinking fountains, increasing recycling to really encourage people to bring in your own reusable water bottles. But if you do have plastics, you're recycling it. And what's key is to be pairing more than one waste stream with your recycling. So for example, we always have a landfill bin next to the recycling, or strive to, because that kind of helps encourage better choice making. And when possible, we also have a compost bin there. And when possible, we also have a paper recycling there. So it's important to have these different streams so that the behavior change of knowing how to sort plastic or sort your waste is more kind of inherent. And so including, that kind of change, we've invited green partners, which is our tenants that are committing with us to reduce plastics. We provide green resource guides on our website of different alternative plastics to use. We've updated our permits, so people who hold events in our park, they are not allowed to bring single-use plastics for their events. For example, there's a fashion show and the production team is not allowed to bring, handouts of Dasani water bottles. They need to find an alternative, and we work with them on that. It's not just like a one-way street. And that's kind of, again, the goal of this is that it's a dialogue of finding solutions. And we have tons of education programs. That's kind of my wheelhouse, teaching kids about single-use plastics, being aware of the plastics in our world and where we can make those changes, considering CSOs and how we can reduce water to reduce pollution in our waterways, things like that, and expanding our research. We just conducted a 2-year evaluation of Park Over Plastic to help find what has been the successes of the program and what can we do what are the recommendations for next steps. And all of this is available on our website, hudsonriverpark.org, if you're interested in checking out any of this Park Over Plastic information, the report that just came out, or just our research, our microplastics research, and our marine debris data. We share all of that on our website too, if you'd like to take a look. So yeah, now we have some time for